The mission statement of Orbital Operations, a new space startup, can be summed up in one sentence. Orbital maneuvers in hours instead of months, powered by cryogenic propulsion. In the rest of this video, I will unpack this vision, describing the company's technology, vehicle, and defined use cases. The founders Ben and Ross bring over 15 years of combined experience across various space-related industries. They met at Relativity Space while working on the flight termination system for the Terran 1 rocket. Before that, they had roles at NASA, Aerojet Rocketdyne, SpaceX, and Blue Origin. At Relativity Space, they both contributed to the turbo machinery systems and heat exchangers for the Iron R engine, the new power plant for the company's medium-lift vehicle, the Terran R. The US Space Force is eager to acquire vehicles capable of dynamic space operations. They have emphasized the need to maneuver without regret, a capability that current satellites lack. Today, satellites carry only enough propellant for station keeping and avoiding orbital debris. Shifting between orbits, such as from low Earth orbit to medium Earth orbit, is simply not possible. Orbital Operations aims to change that. Other space startups like OrbitFab are also partnering with the US Space Force to refuel existing assets, extending their operational life and, in the future, enabling in-space servicing and repositioning. Launching a new space asset into orbit can take up to 5 months, a timeline that proves too slow during a crisis. The US Space Force requires high-thrust, high-efficiency vehicles stationed in orbit, ready to execute high-energy maneuvers in hours rather than months. The challenge lies in the fact that such high-energy maneuvers typically demand cryogenic propellants, which are difficult to store due to their tendency to boil off. The technology for long-term in-orbit storage over months or years does not exist, though several companies, including Blue Origin, are actively addressing this issue. Today, the solutions are not great. Storable propellant avoids boil-off but offers poor performance. Electric propulsion is highly efficient but delivers such low thrust that it takes months to achieve what chemical thrusters could achieve in minutes or hours. So what solution is Orbital Operations developing? Let us break it down into 3 parts. First, the Cryo-Cooler, a vital technology for storing high-performance propellant at extremely low temperatures to prevent boil-off. Second, the high-performance rocket engine, and finally, the vehicle itself. To begin, let's look at the fuel Orbital Operations selected for their vehicle: liquid hydrogen. In order for Orbital Operations to maneuver without delay, as they state on their website, it's necessary to build a high-thrust vehicle that can move fast. That vehicle is called Astraeus. This vehicle has evolved a lot since its initial design, but one decision that has been locked in since the earliest designs was the choice of propellants: liquid hydrogen and liquid oxygen. This might be surprising, as hydrogen is notoriously difficult to work with. Remember the SLS vehicle on the launch pad with multiple aborts due to hydrogen leaks? Liquid hydrogen boils off very quickly and needs to be kept at extremely cold temperatures. It also has a tendency to seep through materials, requiring systems be engineered to exacting standards to keep the hydrogen where it's supposed to be. The payoff, however, is exceptional efficiency and thrust. Indeed, liquid hydrogen and liquid oxygen deliver the highest fuel efficiency, as measured by specific impulse, or ISP, of any chemical rocket engine. Orbital didn't start with liquid hydrogen chemical thrusters. First, they looked at nuclear engines, but the engineering and licensing challenges were huge. Then they pivoted to ammonia fuel, but that cut the performance in half. In the end, a nuclear engine using ammonia doesn't give you any more performance than using liquid hydrogen and liquid oxygen in a chemical thruster. Either way, you have to solve how to store hydrogen, but without the difficulty of engineering a nuclear engine. By just focusing on what already works, a chemical thruster using high-performance propellants, they can launch sooner and deliver a high-performance space vehicle that has maneuvering capabilities unlike anything else in space right now. The benefits of hydrogen. Although hydrogen is difficult to work with, and many startups avoid it for this reason, it offers many benefits. High specific impulse. Specific impulse, or ISP for short, is a measure of fuel efficiency. When designing and building space vehicles, the goal is to maximize this value. Liquid hydrogen is, without question, the top performing fuel for chemical engines. It achieves an ISP of 450 seconds, giving the Astraeus vehicle a delta V of 10 km per second. No other fuel can match this level of performance. Their pump-fed propulsion system will deliver 20 times the thrust of any system currently in orbit. Production from water. The propellants can be produced from water, which is abundant throughout the solar system. This wasn't the reason they chose hydrogen, but it's a huge bonus. Orbital Operations plans to launch stable water tanks into orbit, using electrolysis to split the water into hydrogen and oxygen before condensing these gases into cryogenic propellants. A full refueling process takes about 2 months, but once established, the system allows vehicles to dock and top up without waiting for a launch. Compatibility with future nuclear engines. When the space industry gets serious about nuclear propulsion, those engines are going to need hydrogen. Orbital Operations are working on all the needed tech, such as chillers, storage, and feed systems. These systems are mission critical for the Astraeus vehicle and positions them well to service future generations of nuclear-propelled spacecraft. So, what is Orbital Operations actually building? Cryogenic Propellant Management System. According to Orbital Operations, the engine cycle isn't the hardest part. It's hard for sure, but keeping hydrogen cold for years is super hard. To fulfill their mission of performing high-energy maneuvers in hours, mastering this is essential. Without active cooling in orbit, liquid hydrogen would boil off and vent from the tanks within days. As a result, the vehicle would lose all its delta V and maneuvering capability, leaving it sitting there in space. It's not just the temperature though, it's the plumbing. Hydrogen can get past anything. It's a tiny molecule that is very difficult to stop leaking through seals, welds, and valves. To unlock the true potential of liquid hydrogen in orbit, these issues must be resolved. BOREAS, Cryo-Cooler. Orbital Operations has received a letter of support from NASA, giving them access to over 15 years of research and development on cryogenic fluid management. Their plan is to use advanced manufacturing techniques, which likely means 3D printing components for the cryo-cooler. Their plan is to develop a commercially viable 20 Kelvin cryo-cooler. That's a temperature just 20 degrees above absolute zero, needed to keep hydrogen in a liquid state. Potential missions for Astraeus. The Astraeus space vehicle functions essentially as a third-stage rocket in orbit that never returns to Earth. Once depleted of fuel, it can simply be topped up with water, ready for its next mission in a matter of months or even weeks. With launch vehicle level thrust adapted for space, it boasts massive delta V capability. It's fast enough to intercept ballistic missiles in minutes. You can think of each Astraeus vehicle as a refueling station in low Earth orbit, a compact version of the cislunar transporter fuel shuttle that Blue Origin is developing for its lunar landers. Dock, refill, and go. If a space asset cannot reach the Astraeus, the vehicle itself can maneuver to provide in-orbit refueling. This approach offers a simpler alternative to a dedicated propellant depot or a large cislunar transporter designed for refueling lunar landers. The key piece of technology that unlocks this future is cryogenic propellant storage system. The foundation for orbital maneuvering and space defense relies on high-performance spacecraft that can loiter in space for years. That is precisely what Orbital Operations is developing. Their in-house propulsion engine generates over 5,000 pounds of thrust and targets a specific impulse of 450 seconds. Initially, Orbital Operations plans to host government payloads on its vehicles, such as optical and infrared cameras, signal collection equipment, deployable decoys, and weapon systems. Later missions will include rendezvous operations both for military and commercial applications. What has Orbital Operations demonstrated so far? They are deep into engine development and prototyping of their cryogenic propellant management system. Their recent seed round is funding two key technical goals. First, a full-scale, pressure-fed chamber hot fire test of their engine. Second, operational demonstrations of cryogenic systems at both 90K and 20K for propellant storage and management. The initial milestone involves maintaining temperatures at the 90K level, sufficient to liquefy oxygen, which eliminates the majority of heat for both propellants. A later phase will reduce temperatures further to the 20K level required to liquefy hydrogen. Each propellant demands its own dedicated fluid architecture, insulation, and heat rejection system. Comparison with Blue Origin. Blue Origin is also developing a system to store these propellants in space for their fuel shuttle, known as the Cislunar Transporter Vehicle. They're ahead of Orbital Operations, having already built and successfully tested flight prototype hardware at NASA's Johnson Space Center. Orbital Operations Roadmap. Orbital are planning a hot fire test at the end of 2025. This test kicks off the propulsion qualification campaign for their engine. In 2026, they aim to validate their ability to manage oxygen temperatures under space-like conditions. Later that year, they will tackle the more demanding task of controlling hydrogen propellant temperatures in flight-like environments. This cryogenic system is a critical piece of technology that must work. Orbital demonstration phases. Once they have successfully validated the cryo system, it's then time to move on to an orbital demo. This will include a vehicle equipped with all the core subsystems except the engine, serving as a dedicated cryo mission to prove long-term storage of hydrogen and oxygen in a liquefied state. The demo flight will validate key components including tanks, chillers, compressors, heat exchangers, radiators, avionics, and the simulated feed system. This represents the final major milestone before engine integration. Further ahead in 2027, Orbital Operations plans an orbital demo qualification flight. This vehicle will launch into orbit and begin an extended cryogenic operations campaign. During this flight, the company will gather thermal data, assess fluid behavior in microgravity, and refine the guidance and control software. The engine is expected to be fully qualified and flight ready by 2028. Finally, the first demo mission of the Astraeus vehicle, complete with its engine, will occur in 2029. This mission will demonstrate the vehicle's orbital maneuvering capabilities, confirming the expected thrust levels and its ability to perform long-duration, on-demand maneuvers. The ecosystem, competitors, partners, funding, and supply chain. The Astraeus vehicle integrates into the Cislunar ecosystem alongside other space startups, serving both as a potential customer and a service provider. For example, companies like Blue Origin with its Cislunar Transporter and Orbit Fab are focused on shuttling water or water-derived propellants across cislunar space. Orbital Operations could potentially sell water, liquid hydrogen, or oxygen to these companies, as Blue Origin has indicated a willingness to purchase propellants at the right price. Various startups are exploring the harvesting and processing of lunar water ice, which they could supply to Orbital Operations, given that the Astraeus is designed for in-orbit refueling. The company anticipates selling services to the US government, particularly the US Space Force and Department of Defense. These services would also appeal to NASA, which has recently asked for proposals for orbital transport vehicles capable of reaching challenging orbits. With its 10 km per second delta-V capability, the Astraeus is ideally suited to such missions. Furthermore, thanks to its high delta-V, Orbital Operations could offer reboost services to future commercial space stations. Upcoming events. As previously mentioned, Orbital Operations will be busy over the next couple of years designing, building, and testing their cryogenic propellant management system, the critical piece of technology for their company. In addition, they are working on their engine and vehicle. What do you think of their technology and business plan? Is liquid hydrogen and liquid oxygen the propellants of choice for moving in cislunar space? Leave your thoughts and opinions in the comments section below. Thanks for watching. If you enjoyed this space startup video, consider buying me a coffee to help support more episodes like this. The link is in the description. Space News Live is on Saturday evening or Sunday morning, depending where you watch from. The live stream is a great way for you to share your thoughts and opinions on the videos I posted this week or on any space topic in general. I highlight the most thought-provoking comments on videos I've received, along with late-breaking space news and previews of upcoming content. If you got the time, please tune in and say hi. Be sure to like and subscribe so you'll see our upcoming videos. We make videos every week covering the space industry with an emphasis on the smaller space startups that aren't covered so well on other channels. See you soon.